The last reaction that we're going to look at in this chapter is also one of the oldest reactions. This is a reaction that used to be used quite a bit in the early days when chemists were trying to figure out the structure of compounds, and they didn't have access to the modern spectroscopic techniques that we have access to. So the reaction that we're going to study is called an ozonolysis reaction. And from the word ozonolysis, you will hopefully see that ozone is one of the reagents, and the product is where the carbon-carbon double bond has been broken, or lysis, remember hydrolysis, and the two products are aldehydes or ketones. In this case, they're aldehydes. So what happens in an ozonolysis reaction is the ozone cleaves the carbon-carbon double bond and replaces each carbon of that carbon-carbon double bond with oxygens. So back in the day, organic chemists, if they knew that a molecule had a carbon-carbon double bond in it, they would employ this reaction and break the molecule into smaller pieces, which they could then more easily analyze. It is still used today. You will see this reaction employed every now and then. Most of the time, though, organic chemists tend to be more concerned with making bonds, making carbon-carbon pi bonds, making carbon-carbon single bonds, and not breaking them. So this is a little bit of an unusual reaction. We're not going to look at the mechanism, but I do just want to show you some examples. Ozone is not the only reagent. Typically, this is a two-step reaction where ozone is reacted first, and then oftentimes there will be zinc and some sort of an aqueous acid. There are other reactions that are done in the second step. But when you do this, all that happens, once again, is that the carbon-carbon double bond is cleaved, and you form O's, double bond O's on both ends. If you look at the way that I'm drawing this, you will notice that I'm trying to draw things in as similar a shape as they were in the original molecule. If you do this, you will help yourself to avoid making the mistake of miscounting carbons. So let's look at some other examples. This can take place in a cycloalkene. So if I react with ozone and then with zinc and H3O+, once again, what I want to do is I want to try to draw my carbons in as similar a position as I did before. And put double bond O's on each of the carbons that were originally the carbon-carbon double bond. So for instance, if I do 1, 2, 3, 4, 5, I have 1, 2, 3, 4, 5. If you draw things in as similar a shape as possible, then you will avoid having to actually manually count the carbons. So if you see a product that looks like this, and you know that it was formed from an ozonolysis reaction, then all you have to do now is you just stick the pieces back together again. So you just sort of mentally rotate this one around and move it up to there and join this carbon with that carbon and erase the double bond O's so that the reactant will look like that. There'll be other opportunities to practice on the homework. You can have more than one carbon-carbon double bond. So for instance, if I start with this compound and I react it with ozone and zinc and H3O+. Now I'm going to be breaking these two carbon-carbon bonds, carbon-carbon double bonds. All the other bonds stay intact. So the product will look like, if I draw the top piece, here are the the 4 carbons from the top piece. This carbon was once part of a carbon-carbon double bond, so it gets a double bond O. And this carbon was once part of a carbon-carbon double bond, so it gets a double bond O. The bottom, there are the 3 carbons from the bottom piece. This carbon was once part of a carbon-carbon double bond, so it gets a double bond O, as does that carbon.